So today we're going to take our discussion of slope into the real world. And you're going to notice in this section that the heading is called constant rate of change. A constant rate of change just means constant slope. Rate of change and slope are synonyms. Rate of change is just the words we use for slope in a real world example. So today we have really two ideas. We're going to look at a relationship in a table or on a graph, and we're going to ask ourselves, does it describe a linear relationship? And that's, we're going to use our slopes. If the slope stays the same all the way through the table, then it has to be a line, because remember that the steepness of a line, oh, by the way, the slope doesn't change. When it's a line, it goes up at a constant rate. And that's exactly what we're talking about today. The other thing we're going to bring back from 7th grade is a relationship proportional? And maybe you don't remember that word, or it seems far back, or maybe it wasn't covered. I promise we will look at it today. So two things: linear question mark, proportional question mark. So before we go anywhere, let's just review a little bit of vocabulary. And so I have some words hidden here. What are these called? A comparison of two numbers or quantities by division. What is this called? I'll give you a clue. It begins with the letter R. And hopefully you remember that that is a ratio. So 2 to 4, 2 to 4, 2 over 4. These are all ratios. Yes, a fraction is a ratio comparing a numerator to a denominator. If the two numbers have a common factor, like look at the two 4s, then what we just said here, our ratio, can be written in, what happens when you go from 2/4 to 1/2? What is that called? And do you remember that that is simplest form? You reduce it, you write it in simplest form. So we're going to keep talking about those ideas today. Now let's go one step further with these ratios. Let's say a ratio has two different quantities in the real world. So like you're buying apples and it's $5 for 2 pounds, or 130 miles you drive in 2 hours. So when you have a ratio that has two different units, it's more special than just calling it ratio. The word also begins with an R, though. It is a rate, a rate. So dollars per pound, miles per hour. We've got two different units, and that's a rate. Let's take this rate word and now talk about it being simplified so the denominator has 1. So not $5 for 2 pounds, but $2.50 for 1, the 5 divided by 2. Not 130 miles in 2 hours, 130 divided by 2, 65 miles per hour. Do you remember what these are called when the bottom number, the denominator, is 1? And it is a unit rate. So if we use those two terms today, I just want to make sure you remember what they mean from previous years. So we're on page 171, volume 1 book, and there is a table here where Marcus can download 2 songs from the internet each minute. So his internet is working right now that pretty much it looks like every minute, right? He's kind of downloading songs. So compare the change in the number of songs to the time X, and what is that rate of change? Rate, we often think of that as kind of equating to the word speed, and in this case you could use that comparison. What is the speed that these songs compared to the minutes? What's happening? So basically the number of songs is increasing by 2 for every time increase of 1 minute. So 2 minus 0. So for 2 songs, 1 minus 0, it took a minute. Did that rate stay constant? Well, 4 minus 2 is 2 songs in the next 2 minus 1, 1 minute. Did the internet slow up, down, speed up? Let's take a look. 6 minus 4 is 2. Over 3 minus 2, still 2 songs in 1 minute. And what I am calculating is slope, guys. And y minus y, 8 minus 6 is 2. Over 4 minus 3 is 1. And notice that the slope, the rate of change, synonyms, stayed the same all the way across the table. So in this amount of time, the rate that the downloading was happening stayed constant at 2 songs per minute. Now, if you came out here and you had the 5th minute, and there all of a sudden down here it said 9 songs, so you only downloaded 1 song in that minute. Now it is not a constant rate of change. It has slowed down, and things have changed. So just to show you kind of that wouldn't be constant. All right, now they're asking you to draw the graph. So I'm going to ask you to, the video is going to pause and ask you to fill in the labels and plot the points. So if you could do that, we'll come back in a second. Okay, so remember that your X label was time in minutes, and the Y label was the number of songs that we're downloading. Your book is notorious for not putting a title. Be smarter than the book. Let's call it song downloads. So if you didn't write the title in, do that, please. It's really important, and it's the one hang up I have about this book. Okay, the next thing you had to plot 0, 0, 1, 2, 2, 4. And then you'll notice that they all lie in a line. Well, remember that I told you those slopes, 2 songs per minute, that rate of change stayed the same. So because the slope stayed the same from one point to the next that was given, it is linear. The steepness stayed the same. Now remember, if that next minute had only 9 songs, I would have plotted a point right here and the line would start to bend. It would no longer be linear all the way across. So let's just talk about what happened. It is linear. We could tell by comparing the slopes, and we obviously can tell on the graph because if you look at the graph, it forms a straight line. There's no bend, no curve. The constant rate of change, which is the same thing as slope, was 2 songs per minute, rise 2 songs for 1 minute, rise 2 songs for 1 minute, rise 2 songs for 1 minute. That is constant, the constant slope of 2 songs per minute. Now remember, if we had put that 5, 9 here, then it would have been 1 song per minute, and it would no longer be constant rate of change. And then finally, I'm going to use the word proportional here. So you might remember from 7th grade the word proportional. If you look at a graph, it's really easy to tell if something is in good proportion. It has to form a straight line, but there's a second requirement. That line, straight line, has to pass through the origin. So you have to have that sort of 0 minute, 0 songs kind of idea, and that makes it proportional. Now we're going to talk about linear and proportional going forward now. So we're on page 172. Let's start with the word linear. We've just done one, but we're going to keep talking about it. In order for a relationship to be linear, first of all, if you graphed it, you have to be able to draw a single straight line through all the points. And if that happens, it's a linear relationship. Now the question is, I don't want to graph it. So remember that on a table, to determine if something is a line, you're basically going to calculate the slope of all the points connected. So here's your y, so 2 minus 0 over 1 minus 0, so 2 over 1. And then you go to the next 2 points, which would be the 1, 2, and the 2, 4, and you'd calculate the slope, and that would be 2 over 1. And that's kind of what we did on the last slide. Since that rate of change stays the same, your slope stays the same from point to point to point, 5 points, then it is linear. So that's how you check if a table is linear. You calculate the slope. We would have had to done 1, 2, 3, 4 different slopes, comparing points to see if they stay the same. Constant rate of change, in this case, would be the 2 songs per minute. Basically, rate of change is just slope with units. I just noticed that I have a typo down here, so let me fix that. Those 2 letters are right next to each other on the keyboard, aren't they? So anyway, rate of change is the real-world application of slope, and all you have to know is that is slope basically with units. So remember that the change in y over change in x is slope, or the delta y over delta x. These are all slope, and we did that in our last video. So we're just going to keep practicing that as we go forward. Okay, so here's example 1, page 172. And the question is the balance in an account after several transactions. So that means money being put in or money being taken out. That's called a deposit or a withdrawal. So is the relationship between the balance and the number of transactions linear? And if so, find the constant rate of change. Oh, by the way, slope, okay? So we need to find the slope. There's 2 points here, 2 in the middle points, and 2 in the end. And we're going to go down and we're going to calculate slope all the way down. If it stays the same, then we are talking about a constant rate of change, which would make it linear. Okay, so I'm going to take 140 minus 170. That gives me negative 30. And I'm going to take 6 minus 3. So y minus y is negative 30. 6 minus 3, x minus x is 3. And notice that we can divide this to make a unit rate. So in my calculator, negative 30 divided by 3, and many of you wouldn't need the calculator, but that would give me negative 10. So my rate of change is that I am going down $10 for every transaction at the bank. Then I go in again, and will it be another $10 per transaction? Okay, so let's take a look at the 2 middle points. I'm going to take y minus y, 110 minus 140 is negative 30, over 9 minus 6, which is 3, divided out, it's negative 10. And finally, 80 minus 110 is negative 30, over 12 minus 9 is 3, and that gives me a negative 10 too. Mrs. Witter, can I just check to make sure that these keep going by the same amount? It is not just looking at like the y coordinates, it's the ratio. So you have to make sure that the ratio stays the same. So don't just look at those numbers. So notice we are staying constant here with a $10 withdrawal, taking $10 out every transaction. So this would be, yes, it's linear, and the constant rate of change is going down $10 per transaction. Right here, you can see it right there. Okay, so again, don't look at a pattern on the side because they could potentially take out and not have it go every 3 transactions. So the table could have looked like this. And in this case, notice you would have minus 30 and then minus 60. You go, oh, no, if I'm just looking there. But negative 30 divided by 3, remember that was negative 10. Now I'm talking 80 minus 140 would be negative 60. And 12 minus 6 is 6, and I'm still getting a negative 10, and this would still be linear because the rate of change, oh, by the way, slope remained the same. If you can't do those in the head, in your head, use your calculator to calculate, the numbers that I'm showing here. And you have to look at the ratio, not just what the numbers are doing on either side. So on got it A, I'm kind of just trying to show you that by like saying, imagine that this line was missing. So I'm going to pretend on got it A that this line is missing. And the question again is asking, is there a constant rate of change on this problem? So I'm going to take and calculate slope. So this would be my y and this would be my x. Temperature depends on how much time has gone by. We're cooling down a pot of water. So we heated up water, turned off the stove, and now the temperature is dropping. So I'm going to calculate the rate of change. So if I take a look here, 90 minus 95 is negative 5, and 10 minus 5 is 5. I'm going to take the top divided by the bottom to create a unit rate. And basically what's happening is the temperature is dropping 1 degree Fahrenheit for every minute. Does that trend stay constant? So again, I'm just going to ignore this one for a second because I want you to see that the table, what it would look like. Now, if I take 82 minus 90 over 20 minus 10, I'm now looking at negative 8 degrees Fahrenheit for 10 minutes. And I can't tell. I mean, is this the same? It's hard to tell. So I'm going to take the top number divided by the bottom in the calculator, negative 8 divided by 10. And it's now dropping less than 1 degree. See it? It's dropping 0.8 degree Fahrenheit. These are not the same. So what's happening is it was, it's cooling down, and now the rate at which it's cooling down is slowing down. So if we were going to graph this, the points would not fall in a line. It is not linear. So I just calculated the slope between these two and then the next two. And if they're the same, we would have said yay. And if they're not, you would say nay. Okay. Now this one's kind of silly. As far as asking the question, is it linear? The question is, can you connect these with a line? So already I would be saying yes, but the question also wants you to find like a constant rate of change. So if it is linear, we need the constant rate of change. So basically what I'm going to do is I'm going to write these points in a table. So 8 comma 80, see that? 8 comma 80, 16 comma 60, and 24 comma 40, right? So now I'm going to calculate the slope between the first 2 points, the rate of change. 60 minus 80 over 16 minus 8. And when I do that, I get negative 20 minutes for 8 volunteers. So basically what this is telling you is how many minutes a volunteer works. So minutes per volunteer. So there were 80 total minutes volunteered from 8 volunteers, basically. Okay. And yes, we can divide this out. Okay. We'll take a look in a second. 40 minus 60 is negative 20, and 24 minus 16 is again 8. Sorry, I didn't have my mouse in the right spot. And you'll see those are the same. So it is a constant rate of change. So now I don't write the constant rate of change kind of there. I want it as a unit rate. And to find a unit rate, it couldn't be any easier. Take the top number, the numerator, and divide it by the bottom number, the denominator. And that tells you how many minutes per volunteer. Like this is changing. So we are finding that we're losing 2.5 minutes per volunteer. Okay, so that's the first word. To find linear, you have to calculate and make sure that the slopes stay the same all the way across the table. It's easy on a graph, doesn't form a line. Now, we're going to talk about the word proportional. Now, this was a 7th grade word. Like I said, I'm not sure if we're going to remember it, but basically proportional relationships, the two quantities are proportional if they have what's called a constant ratio. So I'm now going to show you an example of that. This is on page 173. And I'm going to go to this example. And as we go along, I'm going to keep asking 2 questions. Is it linear? Is it proportional? I'm going to keep doing those. So first of all, we're going to use the table to determine if there's a proportional linear relationship. Well, it has to be linear to be proportional. So we're going to start there. So what we just did is here's our table. In this particular case, we're comparing Fahrenheit to Celsius. So your X is on the top and your Y is on the bottom. Your book is notorious for putting their tables this way, and it's X comma Y. So 0 comma 32, 5 comma 41, and so forth. Okay. So in order to see if this is a linear relationship, we're going to take Y minus Y, which is 9, over 5 minus 0, which is 5, and I get 9 over 5. And I'm going to check across the table. 50 minus 41 is 9, over 10 minus 5 is 5. Anytime you need to pick up the calculator to check, feel free. 59 minus 50 is 9. 15 minus 10 is 5. And finally, 68 minus 59, yep, it's 9. And 20 minus 5 is 5. Do you see that the rate of change, oh, by the way, slope, stayed the same all the way across the table? So there is a 9 degree Fahrenheit for change for every 5 degrees Celsius. So is this linear? And the answer is yes. Now, to determine if it's proportional, here's where I'm coming up with a new thing, guys. To determine if it's proportional, it's a simple division of y over x, y over x, y over x. Now, the first one isn't going to help us because you can't divide by 0 in the calculator. So let's just skip that for a second. I'll talk about that in a minute. But if you take 41 divided by 5, you're going to see 8.2. Does 50 divided by 10 also give you the 8.2? And the answer is no. So this guy is not proportional. So we check the slopes for linear and just that division of ratio for proportional. Now I'm going to give you another reminder on proportional by looking at this graph. And this is the way that a lot of kids remember what proportional is. So first of all, the graph of a linear relationship is a, shockingly enough, straight line. So if you have a graph asking if it's linear, you just look. Do the points all fall on one straight line? Yes. Now this you might remember from 7th grade. The graph of a proportional relationship always goes through the origin, the point 0, 0. So if we kind of go back to the table, do you see how this was 0, 32? If this had been 0, 0, and this was a line, then it would be proportional. But since it goes for the point 0, 32, it's shifted up from the origin. This is a non-proportional relationship. So yay to linear and nay to proportional. Okay, so we're going to go to a table here. It's our last slide. And we're going to ask our question, is it linear and is it proportional? So the first thing we're going to do is you're going to check your slopes and you're going to see if all the slopes remain the same from point 1 and 2, 2 and 3, and 3 and 4. Now, the way this is worded, they want the mass to depend on the weight in pounds, the mass in kilograms to depend on the weight. So you're going to have your X and your Y. You're going to calculate the slopes, and you're going to answer the question, is it linear? Then we'll come back and talk about proportional. All right, so 18 minus 9 over 40 minus 20, does that equal 27 minus 18 over 60 minus 40? Does that equal 36 minus 27 over 80 minus 60? So this would be the first slope, and you're going to get 9 over 20. Haven't made it a unit rate, but right now I'm just checking to see if it's linear. So 9 over 20. And then here, 27 minus 18 is 9 over, 20. And 36 minus 27 between these 2 points is, 9 over 20. So see how the slopes stay the same from point to point to point to point. So it would be linear. Now, when it asks, for a constant rate of change, 9 divided by 20 in this case would be 0.45 kilograms per pound. So yes, it is linear. And if you could do me a favor, I should have had the units in there, 0.45 kilograms per pound. That would be our constant rate of change. Oh, by the way, slope with units. So yes, if we plotted these points on a graph, they would fall in a straight line because the slope does not change. The rate of change is constant. Right, to check to see if it's proportional, I'm going to pick up my calculator again, and I don't see the origin here, and there is a way to get back, but you know what? It's really easy to just take y divided by x. You're just going to compare the ratios. So take 9 divided by 20. Does it equal 18 divided by 40? And check. All right, so the first one is 9 divided by 20. It's 0.45. 18 divided by 40 is 0.45. And 27 divided by 60 is 0.45. And 36 divided by 80 is 0.45. Hey, Mrs. Wood, if it matches the slope, and you would be very astute in noticing that in that proportional relationship, the slope and that ratio is the same. So is it proportional? The answer would be yes. So if we graph these 4 points, they would fall on a line because the slope remains the same. It's a constant rate of change. And we would know they would go through the origin because it's also proportional because all of the ratios, y divided by x, are the same number. So today we added the idea of rate of change being the same as slope. It's the same idea. They're synonyms. It's just a real world version of slope. And usually we express our rate of change in the real world context as a unit rate. And we're going to talk more about that in our next video. So then we went on to say, can we look at a table or a graph and tell if a relationship is linear? Well, on a graph, it's easy. Is there a single line that goes through all the points? On a table, you have to check the slopes. So between the first 2 points, between the second and the third points, between the third and the fourth points, and if the slope remains the same, it would be a line without even having to graph it. The second thing we talked about today is the word proportional. It's easy on a graph. If you do have that one straight line and it goes through, the line goes through the origin, that one straight line, it's proportional. Well, how do you check that without a graph? You just take your y coordinate divided by your x coordinate. Your y coordinate divided by your x coordinate. And if that ratio stays the same, it's a proportional. And so we know if we were to graph this table, we know it would be a line, and we know that the line would go through the origin. So we did a little bit of a review of proportional from 7th grade. And we also are just taking this idea of lines and slope a little bit forward into the real world. The next time I see you, we're going to practice these ideas together, and then you will practice on your own. I hope you have a great day, everybody.